Ja, hi and welcome to the 7th lecture in the course Programming and Data Structures at Linnaeus University. The topic for today is algorithms. Algorithms is something of a buzzword today. You often read in the newspaper about the clever search algorithms from Google and genetic algorithms for doing this, machine-based learning algorithm. Yeah, it's basically a description, an ambiguous description of how to solve a specific problem. It can be very simple algorithms and it can be very complicated algorithms. It all depends on the problem. The first non-trivial algorithm is considered to be the Euclidean algorithm. Find the greatest common divisor for two positive integers. He wrote it down about 300 before Christ. A clever way of solving this problem. The word algorithm comes from some Persian mathematician, and I don't dare to pronounce this name. Do we have anyone who wants to? Al-Khwarizmi. Okay. He, about year 800, he writes down descriptions, step-by-step algorithms for how to do addition, subtraction, multiplication, and division. In the Latin word, his name become algarismus, and then from this we have our word algorithm. So it's a Persian guy who is given rise to the name. But in general, we have a problem. In this case, it's a very common problem. How do you wash your hair? If I were asking you how do you wash your hair, you would probably come up with something like this. I start by wetting the hair, then rub in shampoo and rinse it away. However, after this course, you will start to put it like this. In a more structured way, you will present. If someone is answering you a question and you know the answer of it, then you will try to present it as an algorithm. So the structured way of saying it is that we start by wetting our hair, and then we repeat until the hair is clean, rub in shampoo, rinse the shampoo away, and then if it's cold outside, use hair dryer, otherwise let the hair dry by itself. Does it make sense? This is a structured response to this question, how do you wash your hair? So this is an algorithm. It's a precise description of how to solve a problem. Another example is a given number n a prime number. The basic idea here is to check if n can be divided by any of the numbers in the interval 2 to n minus 1. If that is the case, then it's not a prime number. So I do it like this. I say that the first thing that we should check is if we can divide it by 2. And then as long as it's not divisible by test, we are increasing test all the time. This one will stop in two different scenarios. It will stop if it is a prime number and we find something that it can be divided. Or if we reach the number n in the end. In that case, it's not the prime number. So we are repeating this loop until it stops, and then we ask if n is equal to test, then it is a prime number, otherwise it's not a prime number. They are described here in something called pseudo code, but it wouldn't be that difficult to translate this into Java. If I gave you this one, would you handle it in Java? Yeah. I will discuss different ways of presenting an algorithm, but in general it should be straightforward for a programmer to translate it into his or her favorite language. We are saying that an algorithm, of course, it should give the correct result, but it should also give an unambiguous result. Only one result for each input. And if you're providing the same input twice, it should give the same response. Be unambiguously presented, a price formulation that can't be misinterpreted. That means basically, if you're a good Java programmer, you should be able to take the description and translate it into Java code. It shouldn't contain any vague statements like sort them, just like that. It's too vague. Terminate after a finite number of steps. No infinite computation. This is one way to compute the value of p. You can do it in this way, but it wouldn't work as an algorithm because this one involves an infinite number of steps. So for any given input, it should be a finite number of steps that need to be taken until we reach the result. Why do we have algorithms? Why do we write down algorithms for wash your hair, for example? Yeah, and also document solutions. I come up with a clever way of doing it. I don't want you to be able to, or I should remember it myself later on, and I should also be able to communicate it. So document problem solutions and communicate problem solutions. These are the two most important parts. But also you will see that we will be able to compare different solutions, something called time complexity. You could, for a given algorithm, estimate the time needed to complete it. And you can, in this way, you can compare two different algorithms and say that in general, this one is faster than the other one. Also, sketchy algorithms are a good preparation before programming. I will show you a few examples of what I mean by a sketchy algorithm. But basically, before you start to do any programming, you should have an idea. And then you basically are writing down an algorithm for how to solve the problem, and then you actually start to implement it. Problem, sort a deck. How do you sort a deck of cards? Here I present an algorithm, sorting colors. It gives me 4 piles. It repeats for each pile or color, sort them by rank, and then collect sorted piles to a deck of cards. Do you understand what I mean by this algorithm? Is this an algorithm? I wouldn't say that it's unambiguously presented. How do you sort in colors? How do you sort by ranks? It is not a one-to-one translation from this code to your implementation. So I would say that we need to specify a few things here more in detail. So I said, does the algorithm describe an implementation? If that is the case, then you have an algorithm. Otherwise, it's too vague for being an algorithm. Yeah? So it should be rather straightforward for a programmer. He shouldn't have to sort a number of sub-problems that are not specified. He should actually be able to translate it into code, and he should have a solution. How do you describe an algorithm? You can do it basically, well, you can do it in many ways, but you can divide it into 3 different approaches. I can use ordinary text, my first approach for washing my hair. I was just writing it as a text. This is the advantage. Even my father can understand it. He don't know anything about computers, but he can read the text and probably get the idea. If I do it in Swedish, I should say. However, often ambiguous. It is not that easy to write a text describing a more complex solution. So it has often the problem that it's ambiguous, vague, not easy to implement. You can provide it one implementation in, for example, Java. This is not unambiguous at all. It is actually an implementation in itself, and if it works, then it's very precise. If we just know Java, then we know exactly how this algorithm works. The disadvantage of this one is that, of course, it requires knowledge about the language. You would probably by now understand an algorithm written in Java, but if I was writing it in Prolog or some other strange language, you would probably have a hard time figuring out what I was doing. Also, they often contain a lot of non-relevant details. Semicolons, system out, print line, matzin, x. So algorithm description given in a well-defined and ordinary programming language is often contains a bit too much information that are needed. So we are often using something called pseudocode, a mix of ordinary text and programming language, not coupled to any specific programming language, easy to understand for a programmer. and often easy to implement. We are translating it statement by statement to our favorite language. So this is the suggested approach that most people are using. Sometimes you will see that they are hard to understand. They think that they are using well-known notations, but for some other guy it might not be that easy to understand. And people are using a lot of mathematics and logics, and if you're not familiar with that, certain algorithms are hard to understand. They think it's very precise and easy, but you are not good in this, so you think it's rather tricky to understand what they are doing. But in general, this is the recommended approach. 2 examples using pseudocode. I'm just asking you a very simple question here. Can the number n be divided by 3? Here I use something that I call structured ordinary text. Ask user for an integer, denote this integer n. If n modulus 3 equals 0, inform the user it's divided by 3, otherwise inform it by 3. I've taken basically a text and indented it a bit for how to solve it. You can also do it almost like a program, n integer to be tested, and then you have something that looks like a program down here. Both of them are correct. There are no exact rules for pseudocode. It should be structured, it should be unambiguous, and it should be using constructs that most people are likely to understand. If and else people are supposed to understand how they work. Which one do you prefer? The second one?
Yes. Let's try it.
Yeah. People who are interested in program usually prefer this way. The shorter the better is basically the idea. But both are okay. So pseudocode, a mix between programming language and ordinary text, is considered to be more precise than ordinary text, more general than programming language. They are supposed to be programming language independent. However, they are often using certain keywords that all programs basically contain. If, while, for each, and also notations from mathematics and logics are accepted. They must, whatever description you are using, they must be able to handle a sequence, selection, and iteration. Any programming language containing these 3 constructions are what we call Turing complete. That means they are enough. You don't need any methods, you don't need any other constructs. If you have these constructs and the ordinary arithmetic, you can basically solve all the problems that are solvable. Sometimes it takes a lot of time, but they are complete in some sense. Also, algorithms are often presented as procedures. You are submitting something value, and the return value from this procedure or method is the correct answer, your answer of the algorithm. There is a mathematician called Polya. He is also interested in pedagogics. He looked at a lot of people, how they were solving problems. Some of them were successful and others were not so successful in solving problems. And he said that successful problem solving in general involves that we start by understanding the problem. We develop a plan for how to solve the problem. Then we are implementing it. It means implementing it in more general sense. We are making it work. And then we stop and reflect over the implementation. That means check that it's actually correct in some sense. Are you taking this approach when I'm giving you a problem? In general, when you are given a problem, do you take this approach? Yeah, in some way you must have been through these steps. If you come up with the correct answer, you have basically taken these steps. I often think that students are not spending enough time on this part, understanding the problem, and then they are jumping to the implementation part and just start to do a bit of programming and hope that it will end up in some way. And then if they get a result, they are not testing it thoroughly enough. But in general, these are the general steps, and if you are translating it to solving with programming, I would say understand the problem, create an algorithm, implement the algorithm, run and evaluate the result. That means test your code. Do you recognize yourself in this procedure? The algorithm part, do you do that? In some way or the other, you must have done it. Or maybe you are jumping directly to this part and then you are creating this one on the fly, sometimes in a good way and sometimes in a bad way. But in general, I often tell you, the students, that you should have an idea before you start to do the implementation. It's no point start to do any implementation unless you have a pretty good idea for how to solve the problem. So I think this is rather general and maybe to some extent obvious, but I think it's good to have them in mind. If you're using this approach, you will in the long run save time for yourself. Divide and conquer is another approach to problem solving. Basically, it's also called stepwise refinement. You are taking one problem, divided into smaller subproblems, which in turn can be divided into even smaller subproblems. This approach that take a look at it and then some high level say that first I have to do this and then I have to do that and then that. And then you take a look at each one of these parts and attack them. It gives a structure to the problem and to the problem solving. Hopefully smaller and easier subproblems will appear. Also, as a programmer, this small subproblems often fits into a method. So in some way it is also a good way of structuring your program into smaller concrete tasks. I have an example here. Do the dishes. Do you know how to do it? When I was in your age, I was not very good at this. You could say that the description of the problem or the problem solution on a high level is to rinse away the leftovers, do the dishes and clean up. It's my topmost layer of the steps I have to go through. Then I take a look at the second problem, do the dishes, and I say that, okay, how do I do this one? Pour water, add some detergent and wash all the items. But this one is still a bit vague, I think, wash all the items. So further down here I said, okay, how do we wash all the items? Well, repeat until no more items the following steps. Take an item, put it into the water, brush it, rinse, and put it up to dry. And you could probably divide the clean up into smaller steps like this. In general, I think that this is a very good preparation before you solve a problem. Divide it into steps like this. Take a look at them, which one is the most complicated one. Divide it into smaller steps, and in the end you have very small problems that are hopefully very simple to solve. Does it make sense? Do you follow this approach? Or do you use the washing machine approach, which is completely different? What I mean by an instance of a problem. We are often interested in finding the general solution. How do I multiply two integers? That is the general problem. The instance of that problem would be just add two numbers like this. So we are dividing it into the general problem and solving one concrete instance of the problem. How do I add two integers? What is the result of adding 13 and 25? How do I sort a list with names? How do I sort this specific list alphabetically? Of course, you should always begin with solving a few instances. I would say that start with a list like this and then come up with one way of solving this problem. And then you try to generalize this problem into a general solution for how to sort any list of problems. So The key word here is instance of a problem. We are often saying that you should start with an instance of the problem, solve a few of these cases, and then come up with a general solution to the problem. How do we recognize a good algorithm? I can ask each one of you to write down an algorithm for sorting names. You would come up with a large variety of different sorting algorithms. How can we decide which one is the best one? We are assuming that all of them are correct, but can we say something more about which one is the best one?
Time and computing efficiency.
Time complexity, yeah, that's one. It's measuring one thing, but other criteria I would say is, first of all, easy to understand and implement. If each one of you presented an algorithm and I should pick one of them, I would probably pick the one which was simple, not the lengthy one and very complicated one. So if you are selecting between different approaches, I think you should take the simple one to start with. Make it run and see if it works for you. And maybe it's good enough. So it should be simple, clearly written, and well documented. And then we have the efficiency part. The algorithm is efficient. In general, we are saying that it uses resources efficiently. For example, memory, network capacity, and time. Time means basically it's fast. I will talk a bit about an introduction to time complexity here, how you can estimate the time complexity for an algorithm. This is one way of comparing algorithms, but as I said earlier on, in many cases, simple is more important. You need something that will sort 100 names. You have a list of 100 names, and you need to sort them. Do you think efficiency is the most important criteria here? Basically, any non-stupid implementation will sort 100 names in like this. So efficiency is only important when the number of items to be sorted is very large. And then it will make a large impact also. So we will talk about time efficiency and time complexity, but don't remember that there are many other criteria that in many cases are just as important. We will talk about something called asymptotic analysis. We would like to analyze algorithms without knowing on which computer they will execute. Answer questions like, which of these two algorithms are faster if the input size is big? How much will the computation time increase if the size of the input is multiplied by 2? You can think about the sorting algorithm. We are interested in how it behaves in comparing two algorithms, but only in the case if the arrays are large. And also assume that I'm been able to sort 1 million names in 1 second. What will happen if I have 2 million names? Will it explode in time or will it just increase a bit? This is the second one here. The fact that we are interested in large input sizes, this is the asymptotic part of it. We are only interested in how it behaves for large input data. We are not interested in how it behaves with an array of size 10 or something like this. So asymptotic analysis means behavior when the input size is big, and what we will try to present or give a very short introduction to is something called, we are doing a time complexity estimate. So it is an estimate of required computation time. And it also depends on that we have some kind of a size. Find integer in a list, time depends on list size n. Check if n is a prime number, it depends on the size of n, if we were using my previous algorithm. Sort the list, once again, it depends on some size n here. So problems like a get method from an object, get the name of this something. We are not interested in the time complexity. It doesn't come with any input sizes. We are just asking for something. So we are only applying time complexity on more complex computation, and they often have one or more parameters that are affecting the computation time. But basically, we are saying that an algorithm have time complexity n if its computational time is proportional to n. Could you give me a problem that have the time complexity big O of n or order of n? Something that depends on the proportional to the input size.
Adding a new element in the first index on an array. So you have to move.
Yeah, that's one. The prime number that I just showed you. We were doing iteration from 2 up to n. Searching an unsorted list. We have to go through all the elements in the list. All these problems have a time complexity which we are saying to be order n, since the time to do it is proportional to the input size. You will see that many sorting algorithms are order n squared. That means the computation time is proportional to n raised to the power of 2. That means if you are adding a list which is twice as long, it will take how much longer time? 4 times longer time to do it. We are saying order 1 if the computation time is constant. That means it doesn't depend on the input size. We can do it in a fixed number of steps. So this one should not be interpreted as if we can do it in one step. It says that it can be done in a fixed number of steps independent of the size of the problem that we are interested in. So order 1 means just constant. Basic assumptions. Each simple computation takes time 1. Simple operations are this one. In practice, we know that plus is somewhat faster than multiplication, but this is just an estimate. So we say that all these simple operations take just 1 computation to do it. Here I show 2 examples. I have a method called print table. I'm printing the multiplication table, and I give you a number n here, and it should print all the n times n values. This one is obviously n squared. The larger n, the number of items printed will be grow like a square in this case. If I'm printing, if n is 10, I will print 100 values. If n is 100, I will print 10,000 values. So basically, we will look at this one, and then we say, okay, which part here is executed most time? And it is this line of code. This line of code is executed n times n times. So we are saying that the work done here is proportional to n squared in this case. Does it make sense? Search for x in an array of size n. I'm saying that this one is proportional to the size n here. We are iterating over all the elements. Every time we are checking if this one is found. And if it is found, then we run through, otherwise we go false. It might be that we find it in the first element. But we are not interested in the best case. We are always interested in the worst case scenario. So when you should give a time complexity estimate, you should always find out what is the most problematic scenario and base your time complexity estimate on this one. For example, searching for an element in a list, the worst scenario is it's not found in the list. We have to go through all the elements, and then in the end we realize that it's not here. So this is the worst. We are trying to estimate the number of computations needed for the worst case scenario. Assume that we were studying our algorithms in detail, and we were able to write down how time behaves in terms of an input parameter n. That means time in terms of input size n. And we come up with that the time needed to do for a given n is like this. Then we say that it's ordo n. We are not interested in any constant factors. And we are only interested in the term that grows with the highest time complexity. So in this case, assume that we were studying our algorithm, and we could say, okay, the number of computations needed for size n would be this one. We will drop this one, and this one, and only focus on this one, since this is the one that will be the dominating one when n grows. So you need to have a basic understanding of elementary mathematics to decide which one of these are the most important one. You should know, if you have not dropped all the math courses, that for a very large n, this one will be the largest term in this one. Here, it turns out that this one is the largest, so we will say the time complexity is n log n. Over here, which one is the largest one? What? Yeah, this is a... You might think that this one, n raised to the power of 88, this one is very large. But it turns out that this one, in the end, it will grow much faster. In general, you don't have to be a math expert. Almost in all cases... Okay, can you see this one? Ordo 1, ordo log n, ordo n log n, ordo n squared, ordo n cube, and 2 raised to the power of n. This one is the fastest one, constant time. And then they are from the fastest one down to the slowest one. And it turns out that exponential time complexity is always the slowest one. In general, if you have a problem with exponential time complexity, you are in deep trouble. Because you don't have to increase the size that much until the computer runs out of energy, or they become very complicated after a while. Chess. What is the best combination of 10 moves in chess? What is the best combination of 11 moves? It formally explodes after a while. So finding an optimal combination of moves more than 5, the computer cannot handle it anymore, because the possibilities grows very fast after a while. So chess is an exponential problem, for example. So we are happy with this one. This one is also okay. Log n. Have you seen the log curve? It grows very slowly after a while. So it doesn't, if we are adding the input size, make it a few more larger, the time, we have the time here, and we have the input size here. It's after a while, it's almost stabilizes, but it continues to grow, but very slowly after a while. Do you need a break? Well, I need it. So let's be back here in 10 minutes. Okay, let's go on. During the break here, I received a question from one of the remote students, and they said, is time complexity the same as big O? They are related, but I wouldn't say it's the same thing. We are trying to do a time complexity estimate, basically number of required computation, how it depends on the input data. The result is given in a big O or ordo, and using an ordo notation. And the ordo notation says basically we are saying that how it behaves for large input data. We are not interested in finer details and constants. We are saying that for larger input data, the time behaves like n squared or something like this. This is a notation in which we are providing the answer to the time complexity estimate. Okay? I will look at sorting and searching. These are the basic algorithms that all of you should know about. We are doing it all the time. We are searching for things and we are sorting things. Searching means check if a given element is in a list or a data collection in general. Sorting means sort them according to some property, alphabetically by size or whatever we are sorting it in due to. I will show two simple sorting algorithms, one more advanced sorting algorithm that is slightly faster. You see here this one is proportional to the input size squared, and this is n log n, and this you will see in the fourth assignment when we are taking time of doing different computation, that for larger input sizes this makes a lot of difference to sort it in this way. We will also talk about two simple search algorithms, and I will try to outline how you can avoid implementing one sorting algorithm for strings, students, integers, and whatever. You should only need one good sorting algorithm and be able to reuse it for different type of input data. Selection sort is basically the simplest sorting algorithm, and I would say that unless you have more than 1 million elements, this one works fine. Selection sort is that we are always assuming a list with n elements, find the smallest of the numbers and swap place with the first element. Find the smallest of the n-1 last numbers and swap place with the second element. Do you start to understand the idea? So find the smallest element, swap place with the first element. Then focus on this one, find the smallest element and swap place with this one, and then I go on like this. This is called selection sort. In this case, example down here, assume this list, -12 is the smallest, swap with position 0, so then it looks like this. I'm swapping this one with this one. And then -7 is the smallest, swap with position 1. In this case it was at position 1, so we don't do anything. -2 is the smallest, swap with position 2. We are searching through this one. We are searching through this one among these elements over here. Find -2 and swap it on this position. And then we go on like this. Yeah, you will have two for statements. One showing which position we are interested in, and the second for statement running through the remaining positions here. So the time complexity will be what? No, n squared. I could describe it like this. My solution, let L be a list with index 1 to n. Then for each one belonging to this interval, 1 to n-1, this is P is the index for the smallest one, and to start with, the smallest one is the first one. So I start by saying that currently this one is the smallest, P. And then for each element in I plus 1, that means for each element in the remainder of the list, I do the following. If the new element is smaller than the currently smallest element, then I say that the smallest element is from now on in this position. So I'm keeping track of the position for the smallest element. And I go through the entire line here until I have found the smallest element among all these elements. Then swap place. I swap the place between I and P here in 3 steps. Okay? So I am keeping track of the index of the smallest element. So initially I said I equals 0. Then I look for the smallest element. I find it over here. So after this loop, I is 1 and P is pointing to the smallest element. Then I'm just swapping place between these two positions. I store temporarily this one. Then I move the element from this position to this position, and then the temp is moved into this position over here. Any problems with this one? And then I increase here and say, okay, now I'm interested in I equals 1. That means the remainder here, and I do the same thing over and over again. Any problems? The inner loop, this part here is executed, actually, if you want to be exact, it's executed this many times. But this one is proportional to n squared, so we're saying that ordo is n squared. Yeah. So often time complexity is just trying to find which part of the code that are executed most time, and see how many times are we executing this code depending on the input size. In this part, it is this code in here that we are executing. This is the hotspot, the code that we're executing most time, and it depends on 2 loops, so it's n squared. I could implement it in Java. I will not go in detail, but what I'm showing here is just this was my algorithm in some language independent format, and this was how I translated it into Java. It is exactly the same thing that I'm doing here, just translating it into Java. Insertion sort. It's another sorting algorithm. Put the second element in the right place among the first 2. Put the third element in the right place among the first 3. Put the fourth element in the right place among. You understand how it works? I take this one, and basically you are trying to move it here. As long as this one is smaller than this one, then you swap place. In this case, I will swap place 1 time. Then I take 12, and I try to move it in this direction. As long as this one is smaller than this one, I will swap place. But we had 6 and minus 7 and 6 here, so it will stay. I take 2, compare it to this one, and try to move it in this direction until I find a spot where it should be fitted. So you're swapping backwards until you find an element which is smaller than the current element. Did you understand the idea? Assume this list. Put 7 among the first 2. I take this one and try to move here, and I see that this one is larger than mine, so I swap place with it. I take this one. This one is immediately larger than this one, so I will not do anything about it. Then I take 12, and I compare it. In this case, I will move it all the way to the front. You are comparing it with the previous element in the list, and if it is a small, the element you're interested in, if it's smaller than the one to the left, you're swapping them and moving them like this. Yeah. So these are 2 well-known algorithms. I will not show how to implement it because it's a part of assignment 3. I give you a description here, how it works, and you should put it into code in algorithm 3. Or you can Google on it and find 5,000 solutions, but try to do it by yourself. It's more fun. So assume both cases. Assume a list with n elements. The first one was find the smallest number and swap with the first. The second one was swap leftwards until you find the correct position. Which one is better? Can you find a scenario when one is better than the other?
Second.
What?
Second one is faster.
In what scenario?
Sometimes you don't need all the steps.
Yeah.
Only one step.
Assume this one, and we have a already sorted list. it will immediately see that we cannot swap this one. It will immediately see that we cannot swap this one. It will basically just go through the elements once. So for almost sorted lists, this one is slightly faster. But in general, they have the same time complexity. But if you should select one of them, there are a few scenarios where this one is actually slightly faster, but not much. In this case, I would say take the simplest one. If you have one of them already implemented, use that one. Searching. Linear search. The simplest idea, if I give you an array and you should search for a certain element, is to run through it from the start position to the end position and check, do I have this element here? If that is the case, I immediately stop and return the position. Otherwise, I return some number indicating I haven't found it. We must check every element. In the worst case, we don't find the element, and we must check every element in the list. That means this one is ordo n. It's proportional to the size of the list. Do we have better algorithms? No, there is actually no better algorithms. If we don't have a sorted list, that means it doesn't contain any specific structure, we have no option but to start from the first element and go through all of them to check if it's not there or not. I'm saying here, not for an arbitrary list in a single core machine. Of course, if you can start to divide your list in two halves and can run them in parallel, you can do it faster. But in general, if you have only one core in your machine, there is no option but to run through all the elements from the start to the end to look for it. Binary search. Find the list, find n in a list with n elements. Assumption, the list is sorted. Here the elements have a certain structure. They are already sorted, and then we can do it much faster. And the basic idea is to look at the middle element. If the mid element is the one that we are looking for, well, then we are done. We have found it. Otherwise, repeat the search. If the element we are looking for is smaller than the mid element, then we can search in this part of it. Otherwise, we search in the second half of it. So we have an array. We are searching for a certain element, 64. We take a look at the mid element. If the mid element is 64, we are done. We have found it. Otherwise, if this element is larger than our element, then we should repeat the process in this one. And then we search in the middle of this one. So we are in each step removing half of the element, saying that in each step we can say that, okay, it's not in this part at least. This one is much faster. We are saying here that each step or search halves the problem. In one part like this, I have reduced the problem size with 50%. So in each step, I'm reducing the problem size. And so the time to search through n elements is the time to search through n half elements plus some extra work. This turns out to be logarithmic. It's always, when it looks like this, it's always logarithmic. And I will try to motivate it later on. The worst case scenario is, of course, not n not in the list. Then I have to go through smaller and smaller until the list is only one long. I check, is this the one I'm looking for? No, it's not, and then I give up. So the worst case scenario is once again when we can't find the element in the list. This one is much faster than linear search. So if you're often doing search, it might be worthwhile to sort it before you start to search for it. How many halving it steps do we need to take? Well, If the input size is 1, we always can decide whether we have found it or not in just one step. If the input size is 2, we might need to move to the other half and look for it there. If the input size is 4, we might need 3 steps to go through all the elements. If the input size is 8, we need 4 steps. If the input size is 2 raised to the power of p, we might need p plus 1 step to half it and find it. So in general, size as a function of time looks like this, but we are interested in the inverse. So if you take the inverse of this relationship, you will find that time is proportional to the second logarithm of n. So the time complexity for binary search is log n, like this. Did it make sense? And remember my sketch of log n. Yeah. Whether we have 1,000 elements or 2,000 elements, it is just one extra half. We just need to divide it one more time. So in the end, looking for 1 million elements or 1 billion elements, it doesn't matter that much. We need to divide it 3 more times or something like this. So this one is very efficient when we are have a large sizes.
Which axis is time and which are?
This is time. This is the input size. It's always like this. Good question. Did you understand the basic idea here? How would you implement it? It smells a bit of recursion, don't you think? I'm searching in this list by finding the middle one, and then I should repeat it in this list. So then I call the same method one more time, but now with only these elements. Call it until the base case is that the list is size 1 and I have found it or not found it. A non-recursive Java implementation. Binary search, I'm searching in this array, and this is the one that I'm looking for. I start by saying that the first index is 0, and the final index is array length -1, and the mid element, I just gave it a value here, is 0. And then I say, as long as the smaller index is smaller than the maximum index, I do the following. I find the mid element, I find the mid position, I pick out the mid position. If the mid position is the element I'm looking for, we are done. Otherwise, if the element we are looking for is smaller than the mid value, then our new max is mid -1. And I'm repeating the loop like this. Did it make sense? The basic idea was the one that I was showing. We are computing the mid element and picking it out. And if our element we are looking for is found, then we are done. If the element we are looking for is smaller than the mid value, then we should move to the lower half. That means maximum in the next iteration should be mid -1. Otherwise, search in the upper half. That means minimum in the next iteration should be mid +1 in this case. I'm just moving the mid and mean and max index here. Yeah, I think I have it here in a recursive version as well. Once again, we are searching this array after this element. I do it in 2 steps. I say that the mean is 0 and max is array length -1, and then I'm calling the recursive method here. It takes the array, the one that I'm looking for, and the minimum and the max index. So to start with, I'm giving it 0, and this position is my max. And then I call the recursive method. If max is less than mean, then we haven't found it. It's not in the list. Otherwise, compute mid position, extract mid element. If we have found it, then we return true. If the one we are looking for is smaller than the mid element, we are calling this method once again with the same input array, the same element we are looking for, the same mean, but now we have changed the max to mid -1 like here. So we are repeating it with a smaller sample here. And of course the opposite if it's larger than. Do they have the same time complexity? Yes, recursion is just one strange way of doing a loop. And we are doing exactly the same steps here as we did in the previous case, so the time complexity will be identical. We are not gaining any time and we are not losing any time by introducing recursion in this case. This is the third assignment. Merge sort. There are two famous algorithms that are better than quadratic time complexity. They are called merge sort and quick sort. And merge sort is the easiest one. We have an array that we would like to sort. We start by dividing it in two halves. And then each of them we are dividing into two halves. This one also, and then we are dividing it further until we have trivial arrays that are sorted by themselves. Then, while we are merging them, we are keeping them sorted. We are keeping them sorted, and then we are merging this two, and we are keeping them sorted like this. And then we are merging this two, and we are keeping them sorted like this. Do you understand the basic idea? It sounds trivial, but this one is much faster for larger input elements. How many levels do we have here? How many times could you divide a list? Log n. It was the same thing we did in the binary search. How many times can I divide a list into halves? And if the list is n long, I can divide it into log this many times. So the number of levels here, when we are dividing it, this one is proportional to log n. So the number of levels are proportional to log n, and the work we are doing here is actually proportional to the size. We have to go through this list plus this list in order to merge them. So we have log n levels, and in each level we are doing the work n. So the time complexity will be ordo n log n. If you should sketch this curve, what does it look like? N log n. This was my log n curve. Well, compared to a straight line, this one is slower, but it's not much. It's very close to a straight line. Actually, it gets closer and closer. So basically, it is slower than a straight line, but still much faster than quadratic. So if you are about to sort an array of size 1 billion, you will save a lot of time taking this approach. It is a part of assignment 3 to translate this idea into code. I can give you a few hints. Sketch the algorithm for recursive method of merge sort. If array is of size 1, then it's already sorted, so we are returning the array. That's the trivial case. Else, divide array into two halves, left and right. Make calls sort left and sort right. Then they will return a sorted version of right and left. And then merge left and right into one sorted array and return sorted array. Did you get the basic idea? We divide it into two halves. One of them is called left, and the other one is called right. This one contains half of the elements not sorted, the second half of the element not sorted. we are calling merge sort one more time for the left one, it will return a sorted version of it. And the right one will also return a sorted version of it. Then we have to merge them. Then we're on this lower half. And we are merging them together, and then we are returning the results. It will not be that much code, but it's tricky to get it right, I should say. I suggest think a bit, Google on it, there are millions of implementations, but try to do it yourself. It's more fun. What?
In the example where you had a tree, what happened with a 10 in the end?
10.
Yeah, it's the low 10.
We are merging these two lists. That means we should take one sorted list and one sorted list and produce a new sorted list. You are basically looking at the first element here and the first element here. If this one is smaller, then you add it and move the pointer to the next step. So you're keeping an eye on both lists, starting from the left, and always pick the smallest one and move it forward. Yeah. We will ask you to do it for integers. You should always start with sorting integers because you are most familiar with integers. So when you are search algorithms and do sorting algorithms, I recommend you that you try to do it for integers, but of course later on you would like to sort something else. Here I have an array of names. Jens, Jesper, Jonas och Henrik. And I'm calling my own sort algorithm, and of course if I print them out I would like them to come up in alphabetic order. And at least in Sweden we are usually sorting on the second name. And then if they are the same we start to look at the first name. What is needed in order to sort them? How do I sort students or names? What? You need not the number, you need to compare them. You need to be able to say that this one is larger than this one. And how do you do that in Java? Yeah, Java has an interface named comparable that is designed for this one. So if you want to sort something, names, students, whatever, you should implement a comparable interface. And then you should give it to a method. In this case, it was my own method, sort, and it works for anyone, any array containing comparables. It knows how to compare them using the compare method in comparables. So we have solved the problems for integers. How do we do it for name? Students, points, horses, and so on. Important to be able to sort two objects of whatever type, we must know whether one is larger than the other. And in Java, we are doing it by implementing the already existing comparable interface. You are comparing your object with some other object. It gives plus or minus indicating lower, larger than or smaller than, and 0 if they are equal. If you have done it correctly, you can use the available sorting methods, or you can implement your own sorting method, and it should work with any array of comparables. I have an example here. No, this was how to implement comparable for the name. We have the first part and the second part. This is the interface comparable required by the interface. I'm comparing my object with another object. I start by checking if the other one is a name. If it's not a name, then I return -99 here. This is a bad idea. Why? Well, it indicates that this one is smaller than the other one. I should have raised an exception instead. Anyway, I'm comparing my name with some other object, and if it is an instance of name, I swap it to a name like this, and then I ask what is your first name and what is your last name, other first, other last. If other last equals last, then I compare this first name, otherwise I'm comparing the last names. does it make sense. Only if they have the same last name, then I compare the first name. If they are not equal, then I'm comparing just the first names like this. So if you want to sort something, implement comparable and do it like this. And this is not good at all. It usually takes me a few minutes to. Don't. Please be very quiet. This is selection sort with comparable. It looks very much the same as the earlier on. It is only here when I was comparing the size, I was comparing if one was smaller than the other. I'm now using compare to method here. So you will be asked to implement selection, insertion sort and merge sort for integers and strings. I suggest that you start with solving the integer case. Then it will be trivial to translate it into the string case, I think, in the next example. And the same here. We are searching for something. We are searching for one particular object among an array of objects here. We are iterating over the array rather than using the equal sign. We are using the equals method. And if they are equal, then we have found it, otherwise not. So for integers, we are using this type of operators to see if they are the same or if they are smaller than or larger than. For any other type of values, we are using the compare to method to check their size and the equals method to check if they are equal. So you should always, if you are implementing the if you're implementing the comparable interface, make sure that A equals B is the same as compare to is null. Otherwise, your two methods of comparing things are not equivalent. So if this one says that they are equal, well, this one should also say that they are equal. So use the same equals definition in both the compare to method and the equals method. Otherwise, it will often end up in trouble. I think that was. In practice, you will be asked to implement the sorting methods and searching methods. They are already available in the Java library. I mentioned it before, we have two help classes, arrays and collections. This one can be used to search and sort the arrays, and this one can be used to search and sort collections, or lists, for example. They have a method called binary search in a sorted list or array, and they have a method sort that can sort any array or list. They are using a variant of merge sort inside this one. They are speeding it up a bit. You should not use this approach. But it turns out that this idea of dividing it into smaller and smaller halves, it starts to take a bit of time, this final step. Divide it into 1 million arrays of size 1. Then we have to create a lot of new arrays, and it's a bit time consuming. So merge sort, as implemented in the Java library, they take this approach, but when this one starts to get smaller than a certain size, then they switch to another sorting algorithm, sort this one, without dividing it into further smaller and smaller elements. So they are basically using merge sort on a large scale, but in the end here they stop and they don't go through this step. They sort this one to this one, and then they start to merge it on the way upwards. It turns out to be slightly faster. But we want you to do the traditional approach that looks like this. The first exercise, have you seen that I published assignment 3? The first exercise is what every computer science should once in their life implement the Euclidean algorithm, since it is the oldest known algorithm in the world. So we are just asking you to implement the Euclidean algorithm. You should provide two numbers, 8 and 12, and it should come up with the greatest common divisor, which is 6 in this case. You can do it in 10 minutes. I don't know, maybe, no. If you do it in 10 minutes, then you are cheating, then you're copying it from the internet, because there are millions of versions available. But I would prefer you to Google it on Wikipedia and then implement it yourself. Then you will understand the idea for it. And the second one, exercise, is 4 methods: insertion sort, merge sort, insertion sort, merge sort. 1 for integers and 1 for strings. Start with the integers, and then it will be rather straightforward to switch it to strings in this case. It shouldn't be that lengthy. If you start to have code which is more than 50 lines, then you have done something wrong. Both of these can be handled rather in a compact version of it. Do you remember insertion sort? What was the basic idea of insertion sort? Swap backwards is my idea. Compare it with the previous one. Compare it with the previous one. If this one is smaller than this one, then you swap place and you find its position in this approach. So that was the insertion sort, yes. Which was the third algorithm. Insertion sort, merge sort, and the first one that I presented was selection sort. That's it. Any questions? Okay, see you on Wednesday. Bye.